Hello, this is a video about the central limit theorem. Given a population of any distribution and if we take some samples of all size n from the population, then these are the results. Number one, if the population is normal or the sample size n is more than 30, then the distribution of the sample means will be normal. Number two, the mean of all sample means equal the mean of the population. 3. The standard deviation of all sample means equal the population standard deviation divided by the square root of the sample size n. This is the formula. Be aware of this notation, sigma x bar or mu x bar. Now, when you have a problem solving issues, first thing you want to know if you have a single value or you have a mean of x bar. If it is a single value, then this is the z formula that you have to use. However, if you have a mean x bar, then this is the z formula that you have to use. This one is just a modified version of this one. Now, let's look at one example. An elevator has a maximum capacity of 4,000 pounds for every 27 adults. Assume that adult males have weights that are normally distributed with a mean of 189 pounds and a standard deviation of 39 pounds. A. Compute the probability that one selected adult male has a weight greater than 148 pounds or 148 pounds. A. Actually, B. Compute the probability that a sample of 27 adult male has a mean weight greater than 148 pounds. Let's do one at a time. A. Compute the probability that one adult male has a weight greater than 148 pounds. First, since the population is assumed normal and we are dealing with one adult male, then we have a single value, so we need to convert x of 148 into its corresponding z's of negative 1.05, and this is how we did it. Okay, single single value. So we use the formula of z equal x minus mu divided by sigma. X is 140, mu is 189, sigma is 39, and that's how we got the negative 1.05. Now, because we want to know that the adult male has a weight greater than 148 pounds, to get the probability, we need to find the area to the right of x equal 148, or the area to the right of z of negative 1.05. To do this, we want to look at the area on the left of z of negative 1.05. If we do that from table A2, we got the area on the left side to be 0.1469, and so area to the right will be 1 minus the 0.1469, then we got 0.8531. And so the probability that one adult male has a weight greater than 148 pounds is 0.8531. B. Compute the probability that a sample of 27 adult males have a mean weight greater than 148 pounds. Well, this sample size is 27, which is not greater than 30, but because we have the population to be normal, then we can do this. And we also deal with the mean weight. So this is the formula that we will use to compute the corresponding z-score for the mean weight of 148. So we need to convert the value x bar of 148 to its corresponding z-score of negative 5.46, and this is how we did it. We use the formula of z x bar minus mu divided by the division of sigma over the square root of n. And so we know everything. We know x bar, we know mu, we know sigma, we know n, plug it in, and then we got z to be negative 5.46. So the probability that a sample of 27 adult males have a mean weight greater than 148 pounds, denoted by this notation. P of x bar bigger than 148 is P of z bigger than negative 5.46 Remember, this is the corresponding z-score that we just computed. So P of z bigger than negative 5.46 equal 1 minus P of z less than negative 5.46, where P of z less than negative 5.46 is the left area of z equal negative 5.46. And so using the table A2, we know that the left area of z of negative 5.46 is 0.001, and so the probability on the right of z of negative 5.46 is 1 minus the area on the left of z, negative 1.56, actually negative 1.46 will be 1 minus 0.001, and so we have the probability of z bigger than negative 5.46, that is 0.9999. And so the probability that a sample of 27 adult male have a mean weight greater than 148 pounds is 0.9999.